All right, we'll look at a couple more examples in this video. In the previous video, we graphed this function. Something that I didn't talk about in the past video, but something that is always worth noting, is that, yeah, we have kind of this general shape that rational functions will take. Of course, it can differ from this, but a lot of times it will look something similar to this. But if you had forgotten kind of this general shape and you weren't sure how it looked, remember you can always, for any function, pick an x value, for example 1, plug it into the function, so 1 plus 3, that's 4 over 1 plus 1, that's 2, and 4 over 2 is 2. So it looks like when x is 1, y is 2. And I could have plotted that point. And I could have done that for any one of them and gotten a bunch of points on the graph and then sketched the curve through those points. Okay? So if you ever want more detail, you can always plug in different x values into the function and get out different y values and then plot those points. Okay, so something to always remember. Okay, let's look here, 49. 49 is nice because it's already factored for us, so that's great. We know we're going to start by factoring everything, and that's done. The second thing we're going to do is look at our domain, so let's not get going too fast and cancel before we realize that our domain is all real numbers except, does anything make the bottom 0? And the answer is yes. There are two numbers that make the bottom 0. Positive 2 is an issue, and negative 1 is an issue. So positive 2 and negative 1 are excluded from our domain. Everything except those two numbers is going to have a value. Okay, now that we've done that, we can, yes, agree that these x plus 1s will cancel, leaving us with a fully simplified x over x minus 2. So that's nice. This is our kind of simplified version. But because something canceled, and I hope you agree, there is a hole in the graph. So let's realize that there's going to be a hole in the graph at some point x comma y. And where is that? Well, we would set the thing that canceled equal to 0 and realize that this only happens when x is negative 1. So there is a hole at negative 1 comma something. Remember that that y value is what you get when you plug in negative 1 into the function and evaluate. So what's that's going to be negative 1 on top over negative 1 minus 2 is negative 3, and negative 1 divided by negative 3 is positive 1/3. So there is a hole in the graph at the point negative 1 comma positive 1/3. Now I realize the graph's a little small, but you can kind of eyeball it. Okay, so there's a hole in the graph there. Cool. What else? Well, we can find quickly our vertical asymptotes and x-intercepts, so let's do that. The vertical asymptote is what you get when you set the bottom equal to 0 and solve in the simplified version. So when I do, I get x equals 2. So there's a vertical asymptote at x equals 2. Cool. There's going to be an x-intercept when you set the top equal to 0 and solve for x. Realize setting the top equal to 0 and solving, well, it's already solved, x equals 0. So there's an x-intercept at when x is 0, y is 0, right? So there's an x-intercept at 0, 0. Cool. And there's, of course, a y-intercept at 0, 0 as well. Remember, if you want to find the y-intercepts, plug in a 0 for every x. You would get 0 divided by 0 minus 2, or 0 divided by negative 2. And 0 divided by anything is 0. So when x is 0, y is 0. Right? Of course, we've already known that. But there's definitely both an x and y intercept at the point 0, 0. So it will cross through the origin. Let's look for any horizontal or slant asymptotes. Remember, for these, we're going to compare the degree of the top to the degree of the bottom. It looks like, again, the degree on top is 1. The degree on bottom is 1, so the exponents are the same. And when the exponents are the same, we're going to divide leading coefficients and get a horizontal asymptote. 1 divided by 1 is 1. So there's a horizontal asymptote at y equals 1. Let's fill that in. Okay, so we have this. There can only be one or the other, so there's never going to be a horizontal and a slant asymptote. It's always one or the other. Remember, the only time there's a slant asymptote is if it's bigger on top, so in this case there is none. We said we're not going to worry about the range of these functions. I'm never going to ask you that, although it's something that we could figure out. I'm not going to write it down, but in this example the range would be from negative infinity to 1, from 1 to 1.5, realize that's not in the range, and then from 1.5 to infinity. So they're a little bit complicated to find out, but it can be done. It's not that the range of these things don't exist. There's definitely a range, but we're not going to worry about finding it. Int behavior, again, with int behavior, well, let's actually finish the graph here. It looks like we've got a couple dots and some lines, but because we know the basic shape of these things, we know it crosses through this point, and would cross through this hole in the graph if it weren't a domain issue, and is going to eventually fall in line with our int behavior. Okay, and this general trend is trending down to negative infinity. Okay. Technically, I guess the argument is there to be made. Well, how do I know that it goes and hits this point and doesn't like turn around at that point and go up? And the answer is, I guess, that we don't. There's some things we can look at here to see that, but maybe the easiest way would be to plug in a 1 into the function and realize that 1 over 1 minus 2 is going to be a negative number, specifically a negative 1. So we could have plot that point and then realize for sure this thing goes down to negative infinity. As to what goes on this side, maybe the easiest way is to just to pick some random x value, maybe 4. Plug it into the function and get out a y value and then plot that point. So I'm going to do that really quickly. 4 on the top, if I plug in a 4 for x, over 4 minus 2, that's going to be 4 over 4 minus 2 is 2, and 4 over 2 is 2. So when x is 4, y is 2. And then now for sure, we're looking like this. Okay? Because we know that eventually this function has to rest along that horizontal asymptote. We know it has to go through that point according to our analysis, and I guess the option is either it goes up forever or down forever, right? That's an option, up forever or down forever, but again, we know that it can't go down forever here because it would have to cross the x-axis, and we know that that doesn't happen. It only crosses the x-axis at the point 0, 0. So this is what our graph will look like. All right, very quickly, let's write the in behavior. In behavior is always written as the limit as x approaches infinity of f of x equals, and then you fill in the answer, and the limit as x approaches negative infinity of f of x equals, and then you fill in the answer. So in behavior will always look like this. The only difference for functions will be what it actually equals. And for this in behavior, as it goes forever to the right and forever to the left, it's forever approaching a height of 1. It's kind of resting along that y value of 1. Whenever you have horizontal asymptotes, that will be your in behavior. That's always the case. That's kind of why they're called in behavior asymptotes, which is nice. We skipped it in the last example, so let's look at it here. What's this vertical asymptote behavior? Well, if we focus our attention on that vertical asymptote, we realize that there's this line here, right? This vertical line. And the question is, as our function gets closer and closer to this line, how does it behave, right? What's the vertical asymptote behavior? And depending on which side you approach it from, it's very different. For example, if I just focus on the right-hand side of that vertical asymptote, then the closer I get to that line, so if I'm approaching that line, that vertical line, the closer I get to that line, the further positive towards infinity the graph goes, right? There's really two options here. It can get closer to that line and go up to infinity, or it can get closer to that line and go down to negative infinity, right? And certainly, on the right side of that line, it goes to positive infinity. If we focus just on the left side of that vertical asymptote, then again, the closer we get to that vertical line, in this case, the further down the graph goes to negative infinity, right? And we want to be able to communicate that with the proper notation, so here's how we do it. If you're ever writing vertical asymptote behavior, it's always going to look like this. It's going to be another limit as x approaches, that arrow, as x approaches, and then whatever your vertical asymptote is. In this case, we had a vertical asymptote at 2. So the limit as x approaches 2 of f of x. But this is kind of not very satisfying because we just talked about, well, the limit as x approaches 2 is different depending on if you come at it from the right or if you come at it from the left. On one side it goes to positive infinity, on the other side it goes to negative infinity. So we want to communicate that in our notation. You may remember this from pre-cal. If we want to talk about what's going on the right side of 2, we put a little plus sign above the 2. It almost looks like a positive sign in the exponent. If we want to talk about the left-hand side, it'll be the same thing. The limit as x approaches 2 of f of x. But we want to talk about the left-hand side, so we'll put a little minus sign there. So this is saying what's the limit as x approaches 2 just on the right side of 2 or just on the left side of 2? We've already answered these questions. On the right side of 2, on the right side of this vertical line at x equals 2, as you get closer to that line, we go up to positive infinity. On the left side of x equals 2, so as we get closer and closer to that vertical asymptote, the closer I get, the further down towards negative infinity my y values go. And this would be the vertical asymptote behavior. Awesome. Let's do example 50, and then we'll end the video. With all of these, I know I haven't said this, but it's usually a good idea to practice on your own. See if you can't find, the vertical asymptote or the x-intercepts or the domain. A lot of the stuff you can probably find on your own now, so maybe pause the video and see what this graph looks like and try your best. And then you can kind of fast forward to the end and see if your answers are the same as mine, kind of figure out where you went wrong, and then you can correct that in the future. Okay? So that's a good idea. But assuming you've paused it and tried your best, now let's check our answers. So the first thing I'm going to do is factor everything. The bottom is nicely factored in the sense that there's only one factor. The top can be factored as a standard quadratic, and so we're going to look for what multiplies to negative 6 and adds to 1. So what multiplies to negative 6 and adds to 1? So I know 3 and 2, so maybe positive 3, negative 2. 3 times negative 2 is negative 6. 3 plus negative 2 is 1. So that's going to check out. Okay, so we factored everything. Great. Now let's look at our domain. Our domain is always all real numbers, except, in this case, 1 is the only number that's going to give us an issue. Okay, let's look if anything cancels. In this case, nothing cancels. And because nothing cancels, there are no holes in the graph. That's nice. Okay, so already we can go to our next steps, which may maybe be finding the vertical asymptote, setting the bottom equal to 0 in the most simplified version. So there's nothing that cancels, so it's already simplified. So x equals 1 is a vertical asymptote. Let's look at our x-intercepts. Set the top equal to 0 and solve for x. Well, there's two values that make the top equal to 0. And that's going to be negative 3 and positive 2. So there are x-intercepts at the point negative 3, 0 and positive 2, 0. Okay. What about the y-intercept? Y-intercept is what you get when you plug in a 0 for x. It doesn't matter which version you plug it into, so we can do this one. 0 plus 3, that's 3, times 0 minus 2, that's negative 2, over 0 minus 1, that's negative 1. Be very careful as you do this. 0 plus 3 times 0 minus 2 over 0 minus 1. That's going to get us here. 3 times negative 2 is negative 6 over negative 1. So that's positive 6. So when x is 0, y is 6. So it crosses the y-axis at the point 0, 6. We said we're not worrying about range. Okay, let's find what's going on here. Is there a horizontal or slant asymptote? For these in-behavior asymptotes, we know we're comparing the degree of the top to the degree of the bottom. What's the degree of the top, though? The degree of the top is 2, and the degree of the bottom is 1, so it's bigger on top. And remember, Bobo Bata eats DC, bigger on top, there's a slant asymptote. So there is a slant asymptote, which means there's no horizontal asymptote. And we learned how to find the slant asymptote. We're actually going to take the top and divide it by the bottom and get an answer, although we will ignore the remainder. So let's look at what that's going to look like. Take the top, so when we do our synthetic division, we write the coefficients, so 1, 1, negative 6. We're going to use a magic number out here by setting the thing you're dividing by equal to 0 and getting a value. In this case, x minus 1 equals 0, so the solution to that factor is 1. Please remember to be very careful there. A lot of times you're just changing the sign. Bring down the 1, bring down that first number, multiply, 1 times 1 is 1, add, 1 plus 1 is 2, multiply, 1 times 2 is 2, add, negative 6 plus 2 is negative 4. Although we really didn't need to do that last step because we know we're going to ignore the remainder because when you do synthetic division, you always reduce a power. So it used to be x squared plus 1x minus 6. So we reduce a power when we divide, so this is now 1x plus 2, which means this 4 is the negative 4 is the remainder, which we will ignore. So the slant asymptote is the line y equals x plus 2. And that's an easy line to graph. It has a y-intercept at 2 and a slope of up 1 over 1. So this would be our slant asymptote. I'm trying to be very careful with my dotted lines here. Okay. So what should this graph look like? Again, we have a couple dotted lines and a few dots, so not very much detail. I'm not going to do it, but remember, if you wanted to, you could plug in a 3 in for x and get out a y value and plot that point. Plug in a 6 in for x, get a y value, plot that point. Do as many points as you want, but for now, we kind of have enough information here. We know it has to go through this point and this point. Based on this end behavior asymptote, my function will eventually approach this line and never deviate. Okay? But it has to go through this point, and eventually, because it can't cross that vertical asymptote, it's got to go up. We know it can't go down, because to go down it would cross the x-axis, which is not possible. Okay? Same thing here. Eventually, this function will approach this slant asymptote, this end behavior asymptote, and never deviate. And we'll go to our vertical asymptote as well. Okay? So this one takes a unique shape, pretty cool shape, because of that slant asymptote. It's going to look something like that. Okay? I'm not going to do the vertical asymptote behavior, or at least write it out. Hopefully you have written it out, but I will say it out loud. The vertical asymptote behavior is the following. The limit as x approaches 1 from the right is negative infinity. The limit as x approaches 1 from the left of f of x is positive infinity. Okay? The end behavior, so very quickly, the limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. So we just said those out loud. The limit as x approaches infinity, as x gets infinitely large, our y values get infinitely large. And as x gets infinitely negative, so the further left you go, the further down the function goes to negative infinity.